Hello, my dear students. Uh, I'm quite hopeful that you are enjoying my lectures. Although I got many comments regarding that my lectures are not too interactive or not too interesting, but to be very, very truthful, I can't be more interactive or I can't make these topics more interesting. Although, because I have too many facts to share with you, and that facts are voluminous. Means I need to share with you a very important topics and very important facts that are quite large, and for that I don't have too much time, although I will try my best for making my lectures for making my lectures a bit more interactive. So last class, uh, we have discussed three important properties regarding fluids. First is the mass density. So first property of fluid is mass density. Density in Hindi we call it घनत्व. uh, and it is denoted as rho, and it is defined as mass per unit volume. So for a given volume of a substance, the amount of mass of a substance that is present for that given volume, that represents the density of a substance. For example, the unit for density is kg per meter cube. For water, rho of H2O at 4 degrees Celsius, it is 1000 kg per meter cube. Now, for mercury, the density is 13,600 kg per meter cube at normal temperature and pressure. Now, to make it very, very clear, to make it very understanding for my fellow students, suppose we have a volume, suppose we have a box which is, say, a volume 1 meter cube, that means 1 meter length, 1 meter breadth, and 1 meter height. Suppose we fill this box with water, then it will weigh 1000 kg. But instead of water, if we fill it with mercury, the same box will weigh about 13,600 kg. So the 1 meter cube volume of a substance, it contains how many or how much mass of a substance represents the mass density of a substance. Now, it is quite obvious that the density of mercury is quite large. It is about 13.6 times more denser than water. Also, we have discussed about a second property, which is weight density. Now, till now, you might have been quite familiar with the relation between weight and mass. Weight is nothing but m into g. So, if we have density as mass per unit volume, for weight density, we use the symbol W, and it is defined as weight of a substance per unit volume, and it is denoted as m into g upon v. Now, this m upon v has already been defined as mass density. So, the formula for weight density comes out to be rho into g. And following this, we have the unit for weight density as the unit for weight is Newton, and for volume it is the same, that is meter cube. So, we have the unit as Newton for per meter cube. So, what will be the weight density of water? At 4 degrees Celsius, we have the density of water as 1000 kg per meter cube. So, let us consider the same temperature. So, let us see W of H2O at 4 degrees Celsius. So, it will be rho into G. So, the mass density of water is 1000 kg per meter cube, and the value of G is 9.81 meter per second square. So what we have? We have 9810 kg meter per second square upon meter cube, or this kg meter per second square is what we call as Newton. So we will say that the weight density of water is 9810 Newton per meter cube. Now, similarly, you can also find out the value of weight density for mercury. Taking the mass density of mercury as 13,600 kg per meter cube, try to calculate the weight density of mercury. Now, following this, we also discussed about a third property which we call specific gravity. Specific gravity. This was denoted by Sg, or another term for specific gravity is relative density, or RD. Now, as the name indicates, this is a relative term, whereas the mass and weight density, these both are absolute terms. Now, what is the difference between this absolute and relative? Now, when we talk about relative, it means we are talking about the density of a substance in relation to or with respect to some another substance. Means what we are doing, we are comparing the density of a substance with respect to the density of another substance. To make it more clear, let us see it in more detailed form. Suppose, let us first define specific gravity. Sorry, third, specific gravity. Specific gravity, denoted as Sg, which is nothing but the ratio between the density of a fluid upon the density of a standard fluid. Now, what is this standard fluid? Now, we know that fluid encompasses both liquids as well as gases. So, the standard fluid will be different for both gases as well as for liquids. So, for liquids, the standard fluid which we take will be water. Water, that too at 4 degrees Celsius, because the density of H2O at 4 degrees Celsius, it is how much? It is 1000 kg per meter cube. Now, as I have told you earlier, there are various values of density at different temperature and pressure. As you may remember, in our last lecture, we have discussed that the density of water at, say, 20 degrees Celsius, it was 998 kg per meter cube. Now, let us take this particular value of water at 20 degrees Celsius and try to find out the specific gravity of water at 20 degrees Celsius. How to find out? So, the specific gravity of water, H2O, at 20 degrees Celsius, it will be equal to the density of water at 20 degrees Celsius upon the density of water at 4 degrees Celsius. Now, this density of water at 20 degrees Celsius is 998 kg per meter cube upon the density of water at 4 degrees Celsius. It is quite a very simpler value, and this you may get by heart. Till now, you might have got it by heart also. It is 1000 kg per meter cube. Now, this kg per meter cube gets cancelled, and what we get? We get 0.998. So, the specific gravity of water at 20 degrees Celsius, it is 0.998. Now, students, you must remember that whenever we talk about the properties, we also talk about the temperature and pressure. Here, I am always, you can say, I am always focusing about the temperature. I am always talking that the specific gravity of water is at 20 degrees Celsius is 0.998. Why I am doing so? Because see, the properties are very much dependent upon temperature and pressure. The property, say the specific gravity of water, when we talk about the specific gravity of water at 4 degrees Celsius, will be, will it be the same as the specific gravity of water at 20 degrees Celsius? Say, no, it will not be. Because, see, the specific gravity of water at 4 degrees Celsius, it will be calculated as the density of water at 4 degrees Celsius upon the density of standard fluid, which is again the density of H2O at 4 degrees Celsius. Now we have the density of water at 4 degrees Celsius as 1000 kg per meter cube, and the density of water at 4 degrees Celsius, which is the density of our standard fluid, that is 1000 kg per meter cube. So it comes out to be 1. So we have the specific gravity of water at 4 degrees Celsius to be 1 degree Celsius, to be 1, whereas the specific gravity of water at 20 degrees Celsius, it comes out to be 0.998. Now this is a point which you must always remember, that the properties are always defined at a definite temperature and pressure. Because the topic which we are going to discuss next is about this only. We are going to discuss about the variation of the density with changes in pressure as well as in temperature. We know that fluid has a definite mass and volume at a specific temperature and pressure. So we have fluids having definite mass and volume at constant temperature and pressure. When we say that the fluids have definite mass and volume at constant temperature and pressure, this also implies that it will have a definite density at constant at constant temperature and pressure. Now this also implies one more thing. What is that implication? It means that if we change the temperature keeping the pressure constant, the density must change. Or if we keep if we keep the pressure constant keeping the temperature constant, or if we keep the pressure constant and change the temperature, the density must change. And this change in density on account of change in pressure and temperature are quantitatively expressed in terms of two important properties which I have already told you. First is the coefficient of compressibility, and the second is the coefficient of volume expansion. So let us talk about the first important property, which is the coefficient of compressibility. Now this coefficient of compressibility is also called the bulk modulus of compressibility. Bulk modulus of compressibility, or in simpler terms you can also say it compressibility also, and it is expressed, it is denoted by the capital K. Now how it is defined? We define the coefficient of compressibility as at constant temperature K is nothing but the differential change in pressure that is required to cause a differential change in volume per unit original volume. Now we also know that when we change the pressure, what will happen? The volume gets decreased. So here we include a negative sign. So we have K is equal to minus of dP upon dV by V. So we can define compressibility as the ratio of the differential change in pressure that is required to cause a differential change in volume per unit original volume. Now we also know that this density rho is mass per unit volume. Now suppose for unit mass, we may take density as 1 upon V. Now can you differentiate this term density? On differentiating, we will get d rho is equal to minus of dV upon V square, isn't it? I hope might be quite aware of this differentiation. On differentiating of 1 upon V, you will get minus of dV by V square, which you can again rewrite as minus of dV upon V into V. Again, let us rewrite it as 1 upon V into dV by V, or minus of dV by V. Now see, this minus dV upon V, the value of this we can get as d rho upon 1 upon V, which is equal to minus of dV by V, and we have already defined this 1 upon V as our density rho for unit mass. So we can rewrite this as d rho by rho is equal to minus of dV by V. So we will use this for our definition, and we can rewrite our expression for K as minus of dV upon V as dP upon, instead of minus of dV by V, now we can write d rho by rho. So we can also define this coefficient of compressibility as the differential change in pressure that is required to cause a differential change in density per unit original density, that is